As I'm getting older, chip upon my shoulder, rolling through life, you roll over and die. La 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 la, la 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 la, la la la. Missing Hilly John, sad days are gone, remembering things just to tell them so long.
Hi, I'm G, and in this recitation video, we're going to be doing a standard electric potential problem due to a configuration of point charges. Here's the question. Alright. As with most physics problems, we need to start with our picture, so let's check it out. We're told that we have a configuration of 4 charges of equal charge Q, and they're given in the shape of a square with side length W. We're tasked with finding the electric potential at this center point, P. Now, these problems are typically more straightforward than electric field problems because the electric potential is a scalar quantity. We don't have to take directions into consideration or split up any components like we did for the electric field. We know that V is equal to Coulomb's constant, K, times the charge Q over the distance between the charge and the point in space you're considering. And when there's a collection of many charges, this turns into just a sum over all charges Q. So let's see what we can do here. The distance between the charge Q and the point P is the same for all charges. It's this distance R. Now, finding R is going to be the most challenging aspect of the problem, but we'll worry about it in a second. First, let's see that we can get an equation for the electric potential V for all 4 charges. So I'll just label these as 1, 2, 3, and 4, and we'll go around this square. So for the first charge, we have K times the charge Q over R plus, for charge 2, also KQ over R, plus, for charge 3, again KQ over R, and we see that it's going to be the same for charge 4 since it has the same charge Q and the same distance R as the rest of the charges. However, I should note if one of these charges were negative, we would have to take that into account into the equation and put a negative. Not the case here, so we'll continue. This is then equal to 4 of those KQ over R, since we have 4 charges. Now, we know K, it's a constant, and we're given Q. All we need to do is find R in terms of this length W. And so I'll split this triangle up here, and we know these 2 side lengths are W over 2 and W over 2. So using Pythagorean theorem, we see that R is equal to the square root of the first side, W over 2 squared, plus the second side, W over 2 squared. Continuing, we can find that this is going to be the square root of W squared over 4 plus W squared over 4, which is W squared over 2, or more simply, W divided by the square root of 2. So now we have a functioning R value we can put into here. So we'll see we have 4 KQ over, and again R is W over the square root of 2. Now, plugging in what we know K to be is 4 times 9 times 10 to the 9 newtons times meters squared per coulomb squared. There's K. The charges Q are 9.8 times 10 to the negative 9 coulombs. And the length W is 0.96 meters. And then that's divided by the square root of 2. And this ultimately gives an electric potential of 519 volts at the center of that square. Now, for part B of this problem, we consider an outside charge being brought to the center of this square here. That outside charge also has charge Q. So we look at the work being done for such an occasion. And we know that work is equal to the change in potential energy. But we also know that potential energy is just Q times the potential. So this is going to be Q times V final minus V initial. If the charge starts infinitely far away, its potential has to be 0 initially. And so this is just going to be Q V final, which we found in part A. And we know Q to be the 9.8 times 10 to the negative 9 coulombs times the V final we found of 519 volts. And this ultimately gives the work to bring that charge to the center as 5.1 times 10 to the negative 6 joules. Okay, that's all I got for you for this video. Thanks for watching, and we'll see you next time.